previous classes we completed module 3 which spoke about IIR filter design and its realization. So in today's class let us start with module 4 which speaks about IIR filter. IIR stands for infinite impulse response filter. It is called so because the impulse response of this filter will have infinite number of samples. Now if I consider x of n as the input to this filter and y of n is the output, then we can write the difference equation of a filter as y of n, which is equal to b naught into x of n plus b1 into x of n minus 1, similarly up to bm into x of n minus m minus a1 into y of n minus 1 minus a2 into y of n minus 2 minus similarly up to an into y of n minus n. Now let us move y parameters towards left hand side. Let us keep x in the right hand side only. So if I rewrite the equation y of n plus a1 into y of n minus 1 plus a2 into y of n minus 2 plus similarly up to an into y of n minus n, which is equal to b naught into x of n plus b1 into x of n minus 1, similarly up to bm into x of n minus n. Okay. Now to this equation let us apply Z transform. So if I apply Z transform, the equation will be y of z plus a1 into z inverse of y of z plus a2 into z power minus 2 into y of z, similarly up to an into z power minus n into y of z, which will be equal to b naught into x of z plus b1 into z power minus 1 into x of z, similarly up to bm into z power minus m into x of z. Now in the left hand side we can take y of z as a common factor and in right hand side I can take x of z as a common factor. So if I take the common factor, so 1 plus a1 into z power minus 1 plus a2 into z power minus 2, similarly up to an into z power minus n into y of z, so which will be equal to b naught plus b1 into z power minus 1, similarly up to bm into z power minus m into x of z. So now what I am doing is I am trying to find out the transfer function or the system function of an IIR filter. For that we all know the system function is given by h of z, which is equal to y of z divided by x of z. So to get this equation in this form, so what I need to do, I need to move this entire parameter towards right hand side keeping y of z here only, and I can move x of z towards left hand side. So then the equation will be b naught plus b1 into z power minus 1, similarly up to bm into z power minus m whole divided by the denominator term will be 1 plus a1 into z power minus 1 plus a2 into z power minus 2, similarly up to an into z power minus n. Now if I rewrite this equation in a standard form by taking a variable k, I can write this equation as summation k ranging from 0 to m. Why it is from 0 to m? The value is ranging from 0 to m into bk. Okay. So if I substitute the values of k from 0 to m, we get all these coefficients into z power minus k. Okay. Now if I write this equation, so this 1 is a constant term, I will write that as it is, plus, now this entire term I will write it in the form of a summation formula. So I can write this as summation k ranges from, so what is the range of k? Here the range of k is from 1 to n. So here it should be from 1 to n, and what is the coefficient here? A. So I can write it as ak into z power minus k. Okay. This is nothing but the system function of an IIR filter. Now looking into the system function of an IIR filter, what I can conclude? It is having both numerator polynomial as well as the denominator polynomial. So therefore we know a transfer function which has both zeros and poles, so then that particular system is nothing but an IIR filter. So in FIR filter, when we discuss in the beginning classes, the system function of an FIR filter will contain only zeros. Then looking at such kind of system function which has only zeros, we can conclude that it is an FIR filter. Similarly here, if the system function contains both zeros as well as poles, then such systems are nothing but IIR filter. So now looking into this difference equation, what I can say is y of n will depend on how many parameters? It depends on present input, okay. It also depends on past input. X of n is present input. X of n minus 1 up to x of n minus m is nothing but the past inputs. It depends on present input, past input, as well as we have y of n minus 1, y of n minus 2 up to y of n minus n. So it is depending on past output also. So what I can conclude, the present output of an FIR filter depends on three parameters. The first one is present input, that is our x of n. The second one is past input, that is from x of n minus 1 to x of n minus m, and the last one is past output. Okay, that is from y of n minus 1 to y of n minus n. And coming here, y of z is nothing but the z transform of y of n, and x of z is nothing but the z transform of y of x of n, with the help of which we can find out the system function. So this is all about the introduction of an IIR filter. So in today's class, what let us see is, let us see the various kinds of realization of IIR filter. The first concept which we are going to study related to IIR filter is the realization of IIR filter. First I will teach you the realization part, then we will go for design part. Okay. So coming to the realization of IIR filter can be realized using four different structures. The first one is direct form structure. The second one is cascade structure. The third one is parallel structure, and the last one is lattice structure. So these are the four different structures with the help of which we can realize an FIR filter. So in direct form structure we have two types. It is divided into two types. The first one is direct form 1 and the second one is direct form 2. Okay. So in our syllabus we have only direct form 1 and 2 for the realization part of IIR filter. So let us study how to realize a given system function with the help of direct form 1 as well as direct form 2. Starting with direct form structure, so if I write the difference equation of IIR filter, y of n will be equal to minus summation k ranging from 1 to n ak into y of n minus k plus summation k ranging from 0 to m bk into x of n minus k. Okay. So, in the previous few minutes we saw how to expand the summation and how to deduce the system function. So, with the help of this difference equation, if I write the system function, I can directly write the system function as h of z, which is equal to y of z divided by x of z, which will be equal to summation k ranges from 0 to m bk into z power minus k whole divided by 1 plus summation k ranges from 1 to n ak into z power minus k. So, this is nothing but the system function of an IIR filter. So, now if I look into this, I can write h of z as the product of two system function, that is h1 of z and h2 of z, where h1 of z is equal to summation k ranging from 0 to m bk into z power minus k, and h2 of z is nothing but equal to 1 divided by 1 plus summation k ranging from 1 to n ak into z power minus k. So, if I multiply these two things, I will get what is h of z. So, keeping this thing in mind, I will move on to direct form 1 realization as well as direct form 2. Starting with direct form 1. So, we know h1 of z is nothing but equal to this one. I will take this equation. So, we know that h1 of z is equal to summation k ranges from 0 to m bk into z power minus k. We all know h of z is nothing but equal to y of z by x of z. Since it is h1 of z, I can write this as y1 of z by x1 of z, correct? So, now if I cross multiply, I can directly write y1 of z is equal to summation k ranging from 0 to m bk into z power minus k into x1 of z, correct? Now, what I can do? I can expand the summation. So, if I expand and rewrite, y1 of z will be equal to b0 into z power 0 x1 of z plus b1 into z power minus 1 x1 of z. Similarly, up to bm into z power minus m into x1 of z. Clear? Now, if I apply inverse z transform to this, what happens to z power 0? We know anything raised to the power of 0 is 1. So, I can write y1 of z as y1 of n, which will be equal to b0, it remains as it is, z power 0 is 1, x1 of z can be written as x1 of n plus b1, I can write this as x1 of n minus 1 plus similarly up to bm into x1 of n minus m. Now, what I did? I took the first part of h of z. h of z is nothing but the product of h1 of z and h2 of z. Out of this, I took only h1 of z and I deduced this particular difference equation. Now, with the help of this difference equation, I should plot what is h1 of z. Later, what I can do is, I should take h2 of z, I should find out the difference equation for h2 of z, then I need to draw the figure for h2 of z. Then if I cascade those two figures together, we get the direct form 1 structure. If I draw the figure, so here the output is y1 of n and the input is x1 of n. So, I will start with the input x1 of n, okay. x1 of n should be multiplied with b naught and it should be given to a summing point. So x1 of n should be multiplied with b naught and it should be given to a summing point. Then x1 of n is delayed once in order to get x1 of n minus 1. Yes, what I should do? I should delay x1 of n once. This gives us x1 of n minus 1. To this x1 of n minus 1 I should multiply b1. So to this multiply b1 and connect it to a summing point and connect the output of the summing point to the final summing point. Then again if I delay this once, I will get x1 of n minus 2. Again multiply this with b2, give it to a summing point, connect the output of the summing point to the top summing point. So I should perform the same procedure until I get the last value, that is x1 of n minus m, that has to be multiplied with bm. So if this is bm, the previous sample will be bm minus 1. So here we will be having one summing point, connect this to the summing point and connect the output of the summing point to the previous summing points. Okay. So this is nothing but the structure for h1 of z. So this is the structure for h1 of z. Similarly, with the help of h2 of z equation, I should deduce the difference equation. Then to that difference equation, I should draw the figure. Then if I cascade the two figures, we get the overall direct form structure. So for that, and here the output will be y of n. Okay. Addition of all this data gives us y of n. So from the direct form explanation, we know h2 of z is nothing but equal to 1 divided by 1 plus summation k ranges from 1 to n ak into z power minus k. Okay. But what we know? But h2 of z is equal to y2 of z by x2 of z. So if I equate these two equations, I can write it as y2 of z by x2 of z will be equal to 1 divided by 1 plus summation k ranges from 1 to n ak into z power minus k. Now if we cross multiply, I can write the equation as y2 of z plus summation k ranging from 1 to n ak into z power minus k into y2 of z, which is equal to x2 of z. But I want to find out the expression only for y2 of z, so I will keep this in the left hand side and I will move the second term towards right hand side. Therefore, y2 of z will be equal to x2 of z minus summation k ranging from 1 to n ak into z power minus k into y2 of z. So in the next step, what I should do? I should expand the summation. Then to that equation, if I apply inverse z transform, I will get the expression for y2 of n. Let us expand this equation. So I can write y2 of z will be equal to x2 of z minus a1 into z power minus 1 into y2 of z minus a2 into z power minus 2 into y2 of z. Similarly, up to a n z power minus n into y2 of z. Okay. Now to this equation, let us apply inverse z transform. Apply inverse z transform. Therefore, y2 of n will be equal to x2 of n minus a1 into y2 of n minus 1 minus a2 into y2 of n minus 2. Similarly up to an into y2 of n minus n. So did I get the difference equation? Yes. Now with the help of this difference equation, I should start drawing the figure. So here the input is x2 of n and the output is y2 of n. So x2 of n, x2 of n, so x2 of n is directly given to a summing point. Then here is the output y2 of n. So now what I should do? I should delay y2 of n once to get y2 of n minus 1. So y2 of n is here, delay this once, gives us y2 of n minus 1, multiply this with minus a1. So multiply this with minus a1 and connect it to a summing point. Connect the output of this summing point to the top summing point. Okay. Now again, in order to get y2 of n minus 2, I should delay this once, delay this once, gives us y2 of n minus 2, multiply this with minus a2, connect it to a summing point, connect the output of this summing point to the previous summing point. I should perform the same procedure until the last coefficient, that is y2 of n minus m minus y2 of n minus n, which has to be multiplied with minus an, and that should be given to the summing point. And here it will be minus a n minus 1. So this is the structure for h2 of z. Now what I know, h of z is nothing but equal to h1 of z into h2 of z. In control system, when we have two blocks in series, what we do to reduce the two blocks into single block, we multiply the system gain of those two blocks. Similarly here also, we know h of z is nothing but multiplication of two system functions. So if it is multiplication of two system function, what I should do? I can connect the two structures in series. So what I will do? I will connect this structure in series with that structure, which completes the direct form 1 structure. So this was our h1 of z structures. So to this structure I should connect in series the structure of h2 of z. So connect this. So here the output was y1 of n. So here the input is x2 of n. So the summing point, finally we get y2 of n. So where y2 of n is nothing but our overall output y of n, x1 of n is nothing but our input x of n. So now I should delay this. The same structure I am copying it here. Okay. Summing point. Here it will be minus a1. y2 of n minus 1, y2 of n minus 2. So here it is minus a2. The same thing I should perform until the last coefficient. Okay. Here it is minus a n minus 1. Z bar minus 1, y2 of n minus n. Here it is. So this is nothing but the direct form 1 realization of an IIR filter. So whenever they give system function, in order to draw the direct form 1 realization, what I should do is, if we remember the structure, it is easy to draw. So where we should replace, where we should write b0, b1, b2, bm minus 1, bm. Similarly the coefficients a, minus a1, a2, minus an minus 1 and minus an is known, and if the structure is known, it is very easy to draw the direct form 1 structure for the given system function. If I look into the structure, so this is nothing but the structure of H1 of Z. Similarly, this is nothing but the structure of H2 of Z. Since we know H of Z is nothing but equal to H1 of Z into H2 of Z, we connect this in series, okay. And this particular structure requires m plus n plus 1 multiplications, and we perform m plus n additions, and the number of storage units required is m plus n plus 1. So this is all about direct form realization. So now let us move on to direct form 2. If we start with direct form 2 realization, so I have written the system function of an IIR filter. So what I can write is, we know that h of z is nothing but y of z by x of z. So instead of writing it as y of z by x of z, I will incorporate a term, that is y of z by x of z into w of z by w of z. So if I rewrite this expression, I can write it as h of z will be equal to w of z divided by x of z into y of z divided by w of z. From this equation and this system function, if I write, I can write w of z by x of z be equal to 1 divided by 1 plus summation k ranges from 1 to n ak into z power minus k. Similarly, y of z by w of z will be equal to summation k ranges from 0 to m bk into z power minus k. Now what let us do? Let us find out the difference equation for this and draw the structure. Similarly, let us find out the difference equation for this and let us draw the structure. So I'll term this as equation 1 and let this be equation 2. So from equation 1, what I can write? From 1, so what I am doing is I am just cross multiplying these two. So I can write w of z plus summation k ranges from 1 to n ak into z power minus k into w of z will be equal to x of z. Now I need to find out the expression only for w of z because that is the output. So I will move this term towards right hand side. So w of z will be equal to x of z minus summation k 1 to n ak into z power minus k into w of z. Okay. Now let us expand the summation. So if I expand the summation, w of z will be equal to x of z minus ak into z power minus 1 into w of z minus, so this has to be 1, a2 into z power minus 2 into w of z. Similarly up to an into z power minus n into w of z. Now to this equation I can apply inverse Z transform. So apply inverse Z transform, w of n will be equal to x of n minus a1 into w of n minus 1 minus a2 into w of n minus 2. Similarly up to an into w of n minus n. So now I got the difference equation for the first equation, this one. Now let us draw the structure for this. So if I draw the structure for this, here the input is x of n and the output is w of n. So x of n is directly given to a summing point, okay, gives us w of n. W of n is delayed once to get w of n minus 1. Delay this once, gives us W of n minus 1. This has to be multiplied with minus a1. Give it to an adder. Connect the output of this adder to the top adder. Okay. Now again delay this once. Gives us W of n minus 2. So again here I need to multiply this W of n minus 2 with minus a2, connect it to an adder, connect the output of this adder to the top adder. I should perform the same procedure until the last value, and the last value which we get is omega n W n minus n, which has to be multiplied with minus an. Here it will be minus an minus 1. Okay. So this is nothing but the structure for equation 1. Now let us take equation 2, deduce the difference equation, and let us draw the structure. So this is equation 2. I can cross multiply, and if I write y of z will be equal to summation k ranging from 0 to m bk into z power minus k into w of z. Okay. Now let us expand the summation. So y of z will be equal to y of z will be equal to b naught into z power 0. Z power 0 is 1 into w of z plus b1 into z power minus 1 into w of z. Similarly up to bm z power minus m into w of z. Okay. Now to this one let us apply inverse z transform. Apply. So what will be the equation? Y of n will be equal to b naught into w of n plus b1 into w of n minus 1. Similarly up to bm into w of n minus m. Now I got the difference equation. To this difference equation let us draw the structure. Here the input is w of n and the output is y of n. So w of n is multiplied with b naught, okay, and it is given to a summing point which yields us the output y of n. Then this has to be delayed once. This has to be delayed once, gives us w of n minus 1, which has to be multiplied with b1, and that should be given to the summing point. Again if I delay this, gives us w of n minus 2, multiply this with b2, connect it to summing point. Perform the same procedure until we get last sample, that is w of n minus m. Multiply this with bm. So this is the structure for equation 2. Now I know h of z is nothing but h1 of z into h2 of z. So now what I should do? I need to combine these two things to get the overall structure. If I cascade both the structures and draw, I can write it as x of n, give it to a summing point. So this is a w of n. So I need to delay this once, gives us w of n minus 1, which is multiplied with minus a1 summing point, and connect the output of this summing point to the top summing point. Now again I need to delay this. Z power minus 1 gives us omega n minus 2. Multiply this with minus a2. Connect to the summing point and connect the output of the summing point to the top summing point. And here will be minus a n minus 1. Here it is minus an, and the last value will be omega n minus 1. Okay. This was the first structure. I should cascade this with the next structure, that is delay w of n once gives us w of n minus 1, multiply this with b1. So here omega of n is directly multiplied with b0 and it is given to summing point. Connect this to the summing point and connect the output of the summing point to the top summing point, which gives us y of n. Okay. Again delay this once gives us omega n minus 2, multiply this omega n minus 2 with b2 and connect it to the summing point. Connect the output of the summing point to the top summing point. Perform the same operation until the last sample. So here it should be Bm, here it is Bm minus 1. Okay. Here it is omega n minus m. Okay. So here it is omega n minus 1, omega n minus 2. So this is the cascade structure. So if I look here, so this is the first structure, so which I have cascaded with the second structure. So this is the second structure. Okay, H1 offset and H2 offset. Okay, so this is nothing but the direct form to realization of IIR filter. And one more thing here is, if the value of n is equal to m, what happens to the structure? If both are equal, instead of taking separate delay units to delay omega n, I can take single delay unit and I can delay and I can reduce the memory. Yes. So if I draw the structure for the condition when n is equal to m, the structure looks like this. That is, this is x of n. I am writing it as it is. Here is a summing point. Again, here is a summing point. Here was our omega n. Here is z power minus 1. Connected to the summing point, multiply it with a1. Delay this once. Summing point, multiply this with minus a2. Similarly, up to the last value, I should do the same thing. Okay. Here it is minus an, here it is minus an minus 1. Okay. Now I can combine this and I can write when the value of n is equal to m. So if I draw the remaining part, I can draw it like this. Summing point gives us y of n. Here it is b0. So again multiply this with b1. Give it to a summing point, connect it to the top adder, multiply this with b2, connect it to a summing point and connect the output of the summing point to the top adder. So here what we get is omega n minus 1 only, right? Okay, here it is omega n minus 2 and so on. So here multiply it with b of m minus 1, connect it to a summing point and connect it to the top adder. At last, multiply here with dm. So this is the direct form to realization. What is the condition for this structure? So the condition here is when the value of n is equal to m. So this is the must condition to combine the memory units. Okay. So this is all about direct form 1 realization and direct form 2 realization of an IIR filter. So in upcoming classes, let us solve problems on direct form 1 and 2 and then we will move on to design of IIR filter. Thank you.